first of all, thank you everyone for joining this webinar. Today we will focus on MISRA C's key role for the compliance to industrial safety standards. My name is Lavinia Battaglia and I'm, amongst other things, the customer service representative here at BUGSENG. Let me now introduce our speaker, Roberto Bagnara. Roberto is our CTO and chief scientist at BUGSENG, other than a very passionate computer science professor at the University of Parma. Not only, Roberto is also a member of the MISRA C working group and of the International Standardization Working Group of the C programming language. Before turning it over to Roberto, please note that you can write all of your questions in the Q&A section here on the left of your screen. We will leave 10-15 minutes at the end to try and reply to as many of you as we can. All right then, Roberto, I leave you the word.
Okay, thank you very much for the introduction. So let's get started. Here is a plan of today's webinar. I will first talk about some important aspects about the C language, and then I will introduce MISRA C, and I will focus on important points that should be taken into account if one wants to properly understand and successfully adopt MISRA C. First of all, a small disclaimer. I am a member of the MISRA C working group and of ISO working group 14 that standardizes the C programming language. However, these working groups and committees have official way of talking to the public. So today I am speaking in a personal capacity. Okay, so first the question, do you want to program in assembly and reason about your programs in assembly, or would you prefer using C instead? So if you are here, I take it for granted that you want to reason in C. So C is a very popular language. It's still, after almost 50 years from its invention, it will be 50 years in 2022, it's still the most used programming language overall, and in particular for embedded systems. And there are very strong economic reasons for this success. First one is that C compilers exist for almost any processor, from the tiny devices to supercomputers. C compiled code is very efficient and without hidden costs. Without hidden costs, I mean that, setting aside that important topic of multi-core, a C programmer looking at the code can more or less guess how much it takes to execute a fragment. C allows writing compact code. There are many built-in operators, and with limited verbosity, you can express quite complicated things. C is defined by an ISO standard, and what is important for programming embedded systems is that C, possibly using compiler extensions, allows easy access to the hardware. C has a long history of usage also in critical systems, and there are lots and lots of tools that assist people developing software in C. Many of these things, however, as we will see, are in sharp contrast with the safety and security requirements. In this slide, a little bit by joke, we express what is the spirit of the standard to which Working Group 14 has always been faithful. Trust the programmer, let the programmer do what it wants, keep it fast even if it is not portable. So this is problematic. And why is it problematic? So let us introduce the notion of behavior in C. I am referring here to C99, Technical Corrigendum 3, but it's the same also in C11 and C18. First of all, behavior is some appearance or action that is externally visible. So if it is not visible to the external world, then it's as if it doesn't happen. And in fact, the compiler is allowed to systematically adopt the so-called as-if rule, which means the compiler can do any transformation that preserves the observable behavior. Okay, notice that this is not a peculiarity just of C, it's also true for C++ and for other programming languages. It is true for all programming languages that admit an optimized compilation implementation. Because in this as-if rule, we have almost all opportunities for optimization. So let us go through the behaviors which are not fully defined in C. There are several kinds of them. So the most dangerous one is called undefined behavior. It is defined by the standard as something that occurs when you use some non-portable on erroneous program constructs or erroneous data. And the important thing to be understood is that when the program engages into undefined behavior, there is no guarantee at all, absolutely no requirement. The program can do just anything. It may crash, it may exhibit erratic behavior, it may even format your hard disk, okay? And what it happens is that the compiler assumes undefined behavior does not happen. So it is the responsibility of the programmer to ensure that you don't have undefined behavior. And if the program does have undefined behavior, it is a fault of the programmer. Let us see a few examples of undefined behavior. It is undefined behavior when a program attempts to modify a string literal, so a constant of type string. So here we have an example. We have a string literal, hello, with 3 exclamation marks, and the smart programmer believes, okay, I will be less emphatic. Let's erase 2 of these question marks. So the programmer writes a null terminator in position 6 of the string. However, this is undefined behavior. Okay, it is undefined behavior, so the program can do just anything. Why is it undefined behavior? We will see a couple of reasons. So the first reason, I can give it to you now, because string literals may be stored in read-only memory. And if you try to write on read-only memory, some hardware exception will occur, which is completely out of control from the program in a portable way. So anything can happen. Another example is when you use an automatic variable, so a variable that is allocated on the stack without having initialized it first. Okay, this is undefined behavior. And why? Because the C standard leaves it open for each data type apart from the character types to possess trap representations. So bit patterns that are not valid, that cause, for example, an hardware exception when you try to read them. For example, if you have a memory with parity bits. Okay, so here we have an example. We have a main program with a local variable a, which is not initialized. So trying to read it is undefined behavior. Okay, maybe there is a trap representation in the portion of the stack used to store A, and this will have a behavior which is undefined. Let us move to another class of behavior, which is called unspecified behavior. It's better than undefined behavior because it happens when there are 2 or more choices to do one thing, and the standard does not specify which one it is. Okay, it will be one of the sensible options, but you don't know which one. And the standard says that the compiler need not document the choice and need not be consistent with the choice. Here is an example. It is unspecified behavior whether the sub-expression in an expression are evaluated in one order or the other. So here we have the main program that returns hello plus word. So there are 2 function calls. However, whether the first to be evaluated will be hello or word, it is unspecified. So this program has two possible outputs. One is hello world, which is probably what was intended by the programmer, but the program may well print word, question mark, hello, blank. And this is also possible. Notice that the compiler might choose an ordering if optimizations are enabled, another ordering if optimization are disabled, and you can have many identical lines in your program, and the compiler has no obligation whatsoever to be consistent with how it compiles these lines in different parts of the program. Okay, another class of non-completely defined behavior. This is surely known by all of you. It's implementation defined behavior. It's behavior that is unspecified, but in this case, the compiler has to document the choice that is made. So all of you know that in C, it is implementation defined, whether int is, I don't know, 16 bits, or 32 bits, or another number of bits. And there are many, many other implementation defined aspects of the language. So in C99, there are 112 of them. Here we see an example. It's implementation defined whether a plain character, meaning a char, a char type which is not preceded by signed or unsigned, it's implementation defined whether it has sign or not. So this program tries and succeeds to understand this by using the standard macro char min, which is provided by the limits.h header file defined by the standard to understand whether the minimal value for char is 0, in which case it is unsigned, or any other value, in which case it is signed. Now, why is C not fully defined? There are so many undefined, unspecified, implementation-defined behaviors in the language. We are talking about hundreds of those. And we passed over local specific behavior, which is not very relevant to this talk, so I will skip it completely. So the reason why the standardized language is not fully defined is because implementing compilers is much easier this way. And most importantly, because implementing efficient compilers, so compilers that generate fast code is much easier. So let's try to understand why is this the case. So undefined behavior. And another undefined behavior is when an exceptional condition occurs during the evaluation of an expression. And for example, an exceptional condition is overflow in the computation of signed integer. So here is an example. A person reasoning in assembly code could write this function. This function is meant to return 1 if the value passed in V is the maximum possible integer. Okay, and it works in the mind of a programmer thinking in assembly this way. So if V plus 1 is greater than V, it's not the maximum integer. But if it is the maximum 1, I know what happens in the machine. V plus 1 will wrap around, and I will end up with a negative number. And so I will return 1, because it is really the maximum integer. No, this reasoning is wrong in C, because overflow in signed integer is undefined behavior. So the compiler can well compile, and it does compile. If you try your compiler and your compiler has a strong optimization option, you will see that it does compile this as if it was return 0. Okay? Because the compiler assumes V plus 1 cannot overflow. Okay? Another example, we have already seen it. So the program attempts to modify a string literal. We have seen already one reason, because the string literal might be stored in read-only memory. Here we see another reason. The point is that the compiler can merge the memory representation of string literals. For example, if we have a program where we have two literals, one is tail and the other is head tail, then the compiler can store in memory only head tail and return a pointer to the fifth character when it needs a representation of tail. So if you change one string, you change also the other, okay? And this is why the compiler assumes this will never happen. The compiler will reserve the right to merge the representation. So two reasons we have seen already why this is undefined behavior. If literals are stored in read-only memory, another exception that is completely defined by other things that are not that are external to the C language, okay? Or the compiler might merge the string literals, and you, by changing one, you would change also other string literals. Let's see another example, which is very interesting. It's undefined behavior when an expression is shifted by a negative number or by an amount greater than or equal to the width of the promoted expression. If you plan to attend the webinar next week, please take this in mind because we'll see an example of this. So, well, let's divide the thing into two parts. So shifting by a negative number. What would mean shifting a quantity right by -2 position? It might mean we shift it left by 2 positions, but if the language was defined this way, then the compiler would have to insert an instruction to test the negativity of the shift count. In case of negativity, it should take the opposite and reverse the direction of the shift. This is not in the spirit of the language. Okay, so the spirit of the language is if you want to play with negative shift counts, you write the code to do the thing. It's a little bit more difficult to understand what might be the problem in shifting a 32-bit quantity 32 positions to the left. So if one reasons, I don't know, in the way where shift instruction is taught in university or at school, one might say, if I push 32 or more zeros from the right of the result, I should get 0, right? No. Why this? And because there are very popular architectures, for example, Intel 64, on which I'm running right now, and Intel Architecture 32, where the machine instruction that implements shifts, well, the first thing they do is they mask the shift count by retaining only the 5 low-order bits. Why they do this? Because they want to have a hard limit to the execution time of the shift instructions. We don't want to spend milliseconds waiting for a million position shift that we programmed by mistake. So shifting by 32 is the same thing as shifted by 32 masked, which is the same as shifting by 0 position, which is the same as doing nothing. So again, the C language leaves this behavior undefined for speed and ease of implementation. Okay, so this is the spirit of the language whenever it is possible. A high-level construct of the language should be mapped to one machine instruction. Okay, and since there is a variability between the machine instructions in different architectures, this is one of the reasons where we have behaviors that are not specified. Okay, so it's now time to introduce MISRA C. So, but before doing this, let's go with the first poll. So, do you know already MISRA C?
Okay, I just launched the poll.
Okay.
Can I give you a couple of seconds?
Yeah, while you express your choice, I take the occasion to tell you that the paper upon which this webinar is based will be sent to you after the webinar.
Okay, so we've got a good 30%, even more of that, who's using it right now, and the same amount knows it, meaning they used it in the past, and another 30% heard of it, but nothing more than that. And a really tiny minority has never heard of it.
Okay, so this is very good, very good, because it gives me incentive to introduce MISRA C in the best possible way I can. So MISRA C, let's start with the MISRA project. So MISRA C is one of the activities of the MISRA project, which started in the 1990. Originally, it was an emanation of a research program funded by the UK government called SAFE IT. The mission has always been to provide world-leading best practices for safe and secure programming. The project is since many years self-supported. There is a private company that provides project management support. By this, I mean that they make little money by selling PDFs of MISRA C and also hard copies. And they use this little money they make to run the meetings 5 times per year of the MISRA C and MISRA C++ working group and the other working groups that are present in the MISRA project. So here are the 2 original MISRA publications. The first one are the MISRA guidelines, so development guidelines for vehicle-based software. MISRA started in the automotive sector, even though the MISRA standards now are completely independent from automotive application. However, in 1994, this was published, and for many years, they were the only guidelines available in the automotive sector. So they were published more than 10 years before work started on ISO 26262. And the second publication, the one on the right, is the first version of MISRA C, dated April 1998. So here is a picture showing a little bit of the history of MISRA C. At the beginning, Ford and Rover were working on their own in-house development guidelines for the C programming language, and they put forces together under the umbrella of the MISRA project, and this resulted in MISRA C 1998, and MISRA C pretty much influenced all the coding standards that have been developed afterwards. For example, JSF, another proprietary coding standard for C++ by Lockheed Martin, and of course influenced all the subsequent version of MISRA C. Okay, so let's introduce MISRA C 2012, the latest revision. Why we have MISRA C? Let me connect to what we have just seen. So what is very important to understand is that the weakness of the C language comes from its strength. So the good points are tied to the bad points. So there is basically, they come from the same sources. For example, the fact that it is easier writing efficient compilers for almost any architecture, as I explained, is one of the reasons behind non-definite behavior. The fact that it is possible to write efficient code with no hidden costs, this is also because there is no runtime error checking at all. If you want to check access to an array, you program the checks, but the language is not adding any code to do runtime error checking. The fact that there are many compilers, the fact that there is an ISO standard, and the fact that ISO standardizes existing practice is another reason why we have non-definite behavior. If we have 2 existing compilers that implement the same thing in 2 different ways, well, in the pragmatic view, which is proper of the ISO working groups, you cannot tell to one of the 2, you are doing it wrong, you should redo it. So having non-definite behavior is sometimes the only way forward to make progress in the standardization of the language. The fact that it is easy to access the hardware, it's the same reason why it is so easy to corrupt the program state. For example, to overwrite the stack. And the fact that you can write compat code is the same reason behind the fact that the language can be easily misunderstood and misused. Okay, people doesn't know, for example, what are the precedence and associativity rules of several of the operators that are provided by the language. So several features of C conflict with safety and security. What is the solution? The solution that industry adopted is a very pragmatical one. It's called language subsetting. You don't program your systems in C, you program them in a subset of C where the chances of committing critical mistakes are very much reduced. Okay? Language subsetting is mandated or highly recommended by all safety and security related industry standards. Okay, and today the most authoritative language subset for the C programming language is MISRA C, and that is why this is the topic of today's seminar. Okay, so let me start to present the guidelines. The MISRA C is a book, in essence, okay? A book, and the recommendations are presented in the form of guidelines. And guidelines are presented in this way. So there is, first there is a pink strip where on the left we have a unique identifier for the guideline, which is composed by a word, which may be a rule or directive. Many of you maybe are more used about the expression coding rule, okay? However, the rules are only a part of the guidelines of MISRA C. There are also directives. We'll see this in a second. And then there is a very short summary of the rule, which is called the headline. Okay, so what is a directive? A directive is a guideline such that not all the information to judge on compliance is contained in the source code. So it is necessary to refer to requirements, specification, designs, or even the programmer intention in order to decide whether a directive is satisfied or not. Whereas when a guideline is called rule, then it means that compliance only depends on the source code. So in principle, if you know the source code, you are able to decide whether there is a violation or not. So this has, of course, a deep influence on what static analysis tool can do or cannot do. So for directive, static analysis tool may assist a lot in checking compliance, but you have to provide them with further information that they require, because as I said, the code is not sufficient. Whereas for a rule, modulo undecidability, static analysis tools will in principle be able of doing the check all by themselves. An important word about the headline. The headline is just a short summary of the guideline. It is not the guideline. So it's a compromise. Rule 5.6 will say little to many people, even people working MISRA C every day, but if they read the headline, they will understand what the guideline is about. So in order to properly understand a guideline, you have to study the full guideline description. And we now see how this information is structured into MISRA C 2012. First, below the pink strip, there are three attributes. Category is one of mandatory, required, or advisory. Analysis is a pair. The first element may be decidable or undecidable, and the second one is system or single translation unit. The final attribute, which is called applies to, is a set of versions of the C standard. So it's C90 and C99, and with the publication around a month ago of MISRA C 2012 Amendment 2, now we can also have C11. And C11 comprises also C18, because C18 has no new features with respect to C11, so it is considered as a technical corrigendum of C11. Okay, so let's see What is the category? Mandatory, required, or advisory? Mandatory means that if you want to make a claim of compliance to MISRA C, you must comply to every mandatory guideline. So deviation is not permitted, no matter what. Whereas if the rule is as category required, then the code must comply or a formal deviation is required. What is a formal deviation? Is an argumentation where someone explains why the rule or directive can be not followed in a specific situation for certain reason, and a reason should be given why safety is not impacted by not applying the rule in a specific instance. Then there are advisory rules. These are recommendations, so they should be followed as far as reasonably practical. So formal deviation is not required, but at the end of a project, if you want to make a sound claim of MISRA compliance, you should list all the violation of the advisory rule. So you need not give a justification, but you have to list them. Okay. There is no other grading of importance of the guidelines in MISRA C. So it's not true that rules are more important than directives or the other way around. Mandatory are the most important, then required, then advisory. This is the only grading of importance that is mandated by MISRA C. So this doesn't mean that any organization may have its own grading of importance, and it is also possible to recategorize the guidelines following certain rules. Now we have seen that there is a decidability attribute. A guideline is marked as decidable if there exists an algorithm that for each source programs is able to give a yes or no answer in finite time. So, and it is marked undecidable if such an algorithm does not and will never exist. So, unfortunately, as you probably know, most interesting program properties are undecidable. For example, division by zero is undecidable. Buffer overflow is undecidable. And of course, limitation of available resources might be such that a static analyzer employs a non-exact algorithm even when an exact algorithm exists. So it's always important to manage the complexity precision trade-off. Then scope of the analysis. A guideline can be marked as single translation unit if it can be checked by one translation unit at a time. So a translation unit is basically a .c file along with the header files it includes, okay? And otherwise the rule will be tagged as system. This means that it's not sufficient to consider one translation unit at a time. You have to consider more than one translation unit at a time, and most frequently you have to consider the entire system, okay? You can see that all the undecidable rules are also marked as system for this reason. Okay, so I have said that the headline of the rule is just a summary. The rule is explained in depth in the following sections. The most important one is the amplification. This is a more precise description of the guideline, and it is normative. So if you believe there is a contrast between the headline and the amplification wins. Okay, as I said, the headline is just a short summary. Then there is in the rationale an explanation of why the guideline exists. Sometimes rules have exceptions, and so when there is an exception, there is a section that describes under what conditions the guideline does not apply. There always are examples, both positive example and negative example. Sometimes the guidelines are related to one another, and when this is the case, there is a see also section that points you to the related guidelines. And below the pink strip, on the right-hand side, sometimes there are references to the C standard. For example, here we are examining Directive 1.1, which says any implementation defined behavior on which the output of the program depends shall be documented and understood. And the list of implementation defined behaviors in C90 is contained in Annex G subsection 3, whereas in C99 is Annex J subsection 3. Okay, so this gives me the occasion of emphasizing what I said. So for a directive, the information about compliance is not completely contained in the code. So here is a very good example, because the directive says that the implementation defined behavior on which the output of the program depends. This is the part that a static analysis tool can tell you. The static analysis tool can tell you if you depend on some implementation defined behavior. However, the tool can say nothing about the fact whether you documented them properly or if you understand them. So that's why this is a directive. So let me present you just a few examples of MISRA guidelines. So let's start with a rule 1.1. It is required. So if you want to deviate it, you have to do so formally. And it's decidable, it's single translation unit, and it applies to all versions of the language. It says that the program shall contain no violation of the standard C syntax and constraints, and shall not exceed the implementation translation limits. So this might be surprising for someone. One might think, hey, but the compiler will give me a parse error if I am going beyond the syntax or the constraint of the language. This is not true. So not only language features that are outside the supported version of C have not been considered when developing the MISRA guidelines. The point is that a conforming implementation, so a conforming compiler, does not have an obligation to generate a diagnostic, so a warning or an error, when a translation limit is exceeded. What is a translation limit? For example, I don't know how deeply you can nest conditional compilation directive like sharp if or sharp if def. Okay, so the standard says that, for example, for C90, that the compiler has to support at least 9 levels of nesting. If you do 10, you are on your own. Okay, so, and the compiler needs not give you a warning about this. So you might be in trouble without a way of knowing. That is why it's very important to have a separate tool to check for MISRA compliance. Not only this, there are several compilers around that, technically speaking, are not fully conforming, where they do not diagnose constant violations. So they compile code that they should not compile. They should give an error, and they don't give it. So you end up with illegal or surprising object code. Let us see another rules. I will only show a few of them because time is limited. I have chosen a guideline concerning comments, because some people might think, hey, what might be the problem with comments? The problem is this, that in the language, the interaction between / comment and the ordinary /* comments and line splicing is very intricate. So not many people know the details, and it is perfectly possible to do serious damage with this. So here is an example. So the programmer thought writing simply the path of a directory here. However, since this ends in a \, this is called line splicing. Line splicing means that it is as if the call to critical function was written here. So was part of the comment. At the very early stage in the translation done by the compiler, physical source lines are merged into logical source line. And all this program all this fragment you see is a single logical source line, which is commented out. So critical function is not even seen by subsequent stages of the compiler. So it was critical to call it, it will not be called, and you will not know. That's why it's important to have a tool that warns you about these kind of things. Another rule, this time is advisory, has to do with conversion between pointer to object and integer types. So the advice is not to use them. Why? Because integer to pointer conversion may result in truncation when the pointer is not wide enough. You can end up with misaligned pointers, so a pointer that to address some quantities should be on some architecture be aligned on a multiple, I don't know, of 4. And if it is misaligned, then bad things can happen. And the other conversion, so pointer to integer, this can result into integer overflows, again, producing undefined behavior. Nonetheless, it is recognized that, especially for programming embedded system, it is sometimes necessary to convert integers to pointer when you have to deal with fixed address for the access to memory mapped registers or other hardware features. Okay, last rule I will present has to do with unspecified behavior. It says the value of an expression and its persistent side effects should be the same under all permitted evaluation orders. This is undecidable, it's system, and it has to do with unspecified behavior and also with undefined behavior, because as I said, there are ordering of things that are not defined, but if you, within 2 sequence points, modify an object more than once, or you modify it and read it at the same time, then it is undefined behavior. And for the unspecified behavior, here is an example. So it is unspecified whether in function calls the ordering in which the arguments are evaluated is left to right, right to left, or any other possible ordering, okay? So, and in this case, since we are accessing volatile variables, it is unspecified whether we trigger the TCNT1 side effect before or after the other one. Okay, what is the solution? So in this case, the solution is simple. So if you want to comply with the MISRA guideline, you introduce temporary variables and you sequentialize the events in the way you want. Any decent compiler will not let you pay a price for having introduced these 2 temporary variables. Okay, so let's move to the next section of the talk. So understanding MISRA C. So there are a couple of points I want to emphasize. So the first one is that MISRA C is part of a process, okay? Applying MISRA C is not simply having a tool. So MISRA C is a process. It's a process that requires that you have done or you do certain things. So software requirements should be complete, unambiguous, and correct. You have to have a design specification. You have to check several things. And another point that is very important is that MISRA C ideally should be used before code reaches the review and unit testing phase, because otherwise you have to expect a lot of reworking and retesting. Because if you think about MISRA C compliance too late, then in order to have MISRA compliance, you will have to modify the code. And so you may have to redo the review. Some reviews, you have to redo testing, maybe. Okay, so full requirements for the process are outside the scope of MISRA C. And full details about development processes can be found in the functional safety standards that each industry sector has to comply to. For example, I don't know, EN 50128 for railways, okay, or ISO 26262 for automotive. Oh, here is the second poll. So which are the functional safety standards that are more relevant to your work?
Okay, I just launched the poll.
While you express your evaluation, let me draw your attention to the fact that on April 28th, we will be a webinar especially dedicated to an important point in ISO 26262, which I hope is relevant to at least some of you.
Okay, for now, the vast majority has to comply with ISO 26262, so automotive, and we have many in all the options we provided, and some of them, a good 20%, express others. So there is something that we haven't put in the options.
Good. Okay, so another point which is very important, MISRA C is not bug finding. So as I said, MISRA C cannot be separated from the process of documented software development it is part of. Okay, so it has very, very little to do with bug finding. So what is bug finding? Bug finding, I use a tool, the tool finds some bugs, and I am happy. So it's not a bad thing to do. It is always good to remove bugs. We also at BUGSENG produce a bug finder. However, MISRA is a different thing. Why is it different? First of all, because violation of a guideline is not necessarily a software error. Okay, MISRA C is prevention. For example, there is nothing intrinsically wrong about converting an integer to a pointer, especially when I need this to address memory mapped registers. However, since this conversion are implementation defined and have undefined behavior, there is rule 11.4 that suggests avoiding this conversion everywhere apart from the very specific instances where these conversions are both required and safe. And this is a general point about MISRA C. Okay, the deviation process is an essential part of MISRA C. The point of a guideline is not you should not do that. The point is to warn you, look, this is dangerous. You can do this only if it is needed, if it is safe, and if your peer can easily and quickly be convinced of 1 and 2, that it is both needed and safe. If it takes half an hour to explain to your colleague why this is safe, it's not good for MISRA. Okay, it must take a few seconds to understand that this is okay. So one useful way to think about MISRA C and the processes that are around it is to consider them as an effective way of conducting a guided peer review. Okay, in an ordinary peer review, you would be sitting with your colleagues and you will be pointing fingers to the screen and you will ask questions. Are you sure here we are protected against this possibility? Well, with MISRA C and the good tool, it is the tool that will guide you to this peer review. And if you follow MISRA C, you will rule out most of the C language traps and pitfalls: undefined behavior, implementation defined behavior, possible incomprehension about aspects of the language. Another difference between bug finding and MISRA C is the attitude with respect to incompleteness. So bug finders are usually tolerant about false negatives and intolerant about false positives. If you watch closely, as I do, the developments of the GNU C compiler and of C-lang, you will see that as soon as there is a false positive report, they will do anything to switch it off, even though if they by doing so, introduce false negatives. Okay, false negatives means there is an issue, but the tool doesn't report it. So this is not the right mindset for MISRA C. MISRA C has to do with the development of safety critical system or systems that are critical in other way, mission critical, security critical. Okay. So false positives are a nuisance, especially if the tool is bad quality and it has lots of them. But if you have false negatives in a tool, it means you have to do other things in order to make sure that you are safe. Okay. So final difference between MISRA C and bug finding is the importance that MISRA C assigns to reviews of all kinds: code reviews, reviews of the code against design document, reviews of the design documents against requirements. So many MISRA rules have to do with code readability and understandability for this reason. This is not the mindset of the audience who look at bug finders. So this kind of audience has a different philosophy. You program as you want, and the bug finders will find some bugs. Okay. So successful adoption of MISRA C. So tools are essential. Of course, it is theoretically possible to manually check everything, but doing so for MISRA C is, of course, enormous. So tools are highly recommended to at least semi-automate the check for compliance. Of course, there are manual activities that remain, so you have to configure the tool correctly, and then you have to configure the tool to capture the deviations. I've said that deviation is an essential part of MISRA C. So let's start with tool configuration. So as I said, there are 112 implementation defined behavior in C99. So this means that the number of C dialects is enormous. An implementation defined behavior, by definition, can be decided in at least two ways. So this means only with this rough estimation, 5 times 10 to the power of 33 possible dialects. In reality, we can reach a very large number, a larger number. And by comparison, the Alexander star, so this more complicated version of the Rubik cube, has less different positions. So, and what is the problem with this is that not only there are many implementation defined behaviors, but many compilers can implement via options different choices for the implementation defined behavior. For an extreme case, the compiler on the machine where I'm giving the presentation implements via command line option more than 100,000 dialects of C. So many things can be set via command line option. And the important consequence is that if your tool is not configured to capture exactly the dialect you are using of the language, then the result of the analysis are completely worthless. So we have seen many projects where, due to misconfiguration of the tool, the analysis result meant absolutely nothing. So one important aspect, for example, are predefined macros. So all compilers have a complex set of predefined macros that may be influenced by compiler options, and compiler option may be given on the command line, on environment variables, or on file. And if you fail to capture this in the tool configuration, then you may well result in having the wrong code being analyzed. Okay, so your compiler predefines a certain macro, so it compiles a certain section of the code. The tool has not been adapted to this, and so you analyze a different section of the code. Okay, so I skipped this because it's late. I had in mind a demonstration where we will give a webinar precisely on this because it is a very interesting topic. So configuring the tool in a way related to the toolchain is an important issue. In theory, there are three possibilities. The first possibility is that the tool is integrated in the compiler and the linker. So this, in principle, is an interesting possibility because certainly the compiler has all the required information. However, if you look at compilers that have a MISRA checking capability, you will see that they are not very good. Actually, they are very bad. And there are several reasons, part of which are economic. And the most important reason is that for the analysis, they reuse the same algorithm used for optimization. And the algorithm used for optimization in the compiler are governed by heuristics. For example, they will not even consider inlining a function that is longer than, I don't know, 5 lines, okay? So, and the heuristics are such that certain analyses are not even run on certain parts of the code because of these heuristics. So, in the end, you will see that these tools have lots of false positives and false negatives. The other possibility is that the tool assumes that you carefully configure it. So this is very error prone. It's a very difficult configuration. And if someone then changes the compiler option for the project, you have to redo the configuration. And there is a third possibility, of course, in that the tool is smart enough to completely avoid this problem. So to configure itself in a completely automatic way and transparent to the user, to take into account the peculiarity of the toolchain in the way you are using it. So this is, of course, the direction we have chosen, and we have been very successful at this, but this is not the topic of this webinar. Okay, final thing, competence. So the importance of training. In fact, if you look at MISRA C, you will see that staff competence is a crucial requirement, and it is also mandated by several functional safety standards. So it is very important that the personnel has been trained, because without proper understanding of the C pitfalls and of the MISRA guidelines, developers risk to perceive the adoption of MISRA as a useless burden. So they may well misunderstand the messages output by the tool and ask themselves what are they supposed to do or not. They will not be able to recognize false positive unless they have received proper training. And they, in the worst case, they may engage into trial and error changing of the code in a desperate attempt to silence the tool. And this will typically decrease the quality of the code. Okay, so third and last poll. Do you have plans in your organization to adopt MISRA C or MISRA C++ in the future, or you are doing it now? And while you express your situation, I draw your attention on a seminar that is similar to the one that we have done today, but it will be based on MISRA C++, and it will talk also about the ongoing merge with AutoSAR C++ 2014. So if you are interested in C++, or if you have colleagues that might be interested, please share the word that we will have a webinar on this on May 14th.
Okay, in the meantime, the 55%, so the vast majority expressed that they are working now on projects that are meant to comply with MISRA C, and the other greater percentage is the 15% that will have to comply within 12 or more months, and the other ones are split between 3 months and 6 months.
Okay, for those who have chosen no, maybe for your organization, MISRA C is too much. So please consider the adoption of BAR C 2018. In the post-webinar mailing, you will receive the link of a webinar we did on BAR C 2018, which you can see in order to understand whether BAR C might be the option for your organization. So conclusion, C is the most used language for programming of embedded systems for very good reasons. The language has advantages and corresponding disadvantages. So the only sensible way to deal with it is by language subsetting. Okay, MISRA C is the most authoritative subset of C for the development of high integrity embedded system, and it is an integral part of a software development process that has very little to do with bug finding. Good tools and proper formal training of personnel is essential for a smooth and successful adoption of MISRA C into any organization. And I'm ready for your questions if you have.
All right, so I'm going to answer one question because Manfred asked if it's possible to watch this webinar again. So if you missed one of our previous webinars, or if you want to watch this again, or just to share them with your colleagues, all our webinars will be available, and the previous one already are, on our YouTube channel. So I'll make sure I'll send you the link in the post-webinar mailing. Another question, MISRA C is addressing mainly the human factor related to human error-prone programmers. But what about automatic code generators, namely software producing software?
Okay, so this is a very good question. I do not completely agree with the fact that MISRA C addresses mainly the human factor. However, there are several rules that have to do with code readability and understandability. And this, of course, does not apply to auto-generated code. However, auto-generators have bugs. And in fact, in safety critical sectors, you have to subject auto-generated code to MISRA C compliance. And it is not so uncommon to find that a bug in an auto generator generated, for example, an instance of undefined behavior. So said that, there are two things. MISRA C has special provisions for auto-generated code. So when you have a portion of code that is auto-generated, you are facilitated in providing deviation for this code. And also there is the notion of deviation permit, which is a topic I couldn't explore. However, you can have deviation permits that you can develop in-house or that you can take from, for example, MISRA C 2004. The MISRA C working group is working at permits for MISRA C 2012, in which the fact that code is auto-generated plays an important role. Said that, you need not wait for the MISRA C working group to produce the MISRA C 2012 deviation permits. You can write your deviations yourself. For example, if you have to do with a MISRA guideline that does not result in undefined behavior or unspecified behavior, and whose rationale is about code readability, understandability, possible developer confusion, you can write very easily your deviation, explaining that the code generated automatically is not required to be read or maintained by any human.
All right, thank you, Roberto. Another question is it possible to get the full set of the slides?
Yeah, of course. To those who require the slides, we can provide them confidentially. So we would like to avoid people redistributing them, but it's okay. If you want to present them in your organization, please let us know.
All right. Another question is from Clayton. Can I program in C11 or C18 and still claim MISRA C compliance?
Yes, in February this year, the MISRA C working group has published the MISRA C 2012 Amendment 2, which extends the language support to C11 and C18. So in the post-webinar mailing, we will send you a pointer to where you can download your copy of MISRA C 2012 Amendment 2, and it is immediately usable. Concerning tools, as I said, this amendment was published in February, so less than 2 months ago. The next version of Eclair, which is our static analysis tool, will have full support for this amendment starting from the next release, which is due to be out in early May.
What's the audit flow for MISRA C compliance?
I'm not sure I fully understand the question, so let me try to give an answer. There is a process that has to be followed in order to do a proper claim of MISRA compliance. The document is called MISRA Compliance. It was released the first time in 2016. In 2020, the MISRA C working group has published a revision. So in the post-webinar mailing, we will send a pointer also to this document that explains how you can produce a defensible argument of MISRA compliance.
Okay, just another one and then we'll wrap this up. Is it common to lose flexibility and have troubles to implement some functionalities when using MISRA C?
No. The mandatory restrictions of MISRA C, so the one you cannot deviate, are take nothing out of the language. They prevent engaging into sure undefined behavior, into big troubles, but all the other rules which are required and advisory can either be followed or defensively deviated in a way that you can really program anything, but in a safe way.
All right. Christoph's asked, however, what is with using the heap?
Using the heap is the argument of two guidelines of MISRA C. So one says don't use dynamic allocation, and it is something that you may deviate if you want. However, what you have to take into account that is dynamic memory comes with a lot of problems. So the problems have to do with what do you do when you run out of memory? How do you ensure a predictable time of the memory allocation and the allocation function? No, there are several problems with dynamically allocated memory that have to be taken care of. So it is possible to deviate the rules which tell you not to use dynamic memory allocation, and in particular not to use the memory allocation facilities in the standard library, so malloc, free, and so on, because malloc and free are plagued by very severe problems due to the fact that they are very general purpose. So they have to accommodate any allocation, the allocation pattern. So many small blocks, big blocks, and so on. So in particular, they are not easily predictable in their timing. So it is technically possible to deviate the guidelines that recommend against using dynamic memory allocation, but it will be challenging, not because MISRA says it, because you have to have a defensible argument on how you deal with all the drawbacks. Okay, what is your plan B? So what if you run out of memory? What will your application do? Okay, do you have hard real-time deadlines? How do you ensure that your allocation and the allocation functions will allow you to meet such deadlines?
All right. Thank you, Roberto, and thank you again, everybody, for joining us today. Let me just quickly remind you that on April 23rd, so next week, we will run a rather revolutionary webinar. The BUGSENG team has, in fact, come up with the right technology to properly interface Eclair with IDEs and extensible editors, and Roberto will demonstrate these new exciting features in this next webinar. So make sure you don't miss it. If you follow us on LinkedIn, you will easily find the registration link because it's in our last post. So as always, feel free to reach out to us anytime. Also, if you have more questions, feel free to send us an email at info@bugseng.com. So thank you again, and I hope to see you all next time. Bye.
Bye-bye, everybody.